Deep in the rolling hills of southern France, something truly extraordinary is taking shape. It's a project of immense scale and ambition that almost defies belief. Imagine a structure as heavy as the Eiffel Tower, housing a heart hotter than the core of the sun. This isn't science fiction or a matrix simulation. This is ITER, the International Thermonuclear Experimental Reactor, one of humanity's most audacious quests to build an artificial star on Earth and harness its power. The goal: unlock a clean, safe, virtually limitless source of energy for future generations. This is how we learn to command the process that powers the cosmos. The challenge is monumental. We are attempting to replicate the sun's fusion process here, on our tiny planet. The sun uses sheer size and immense gravity to crush hydrogen atoms into helium and release staggering energy. We don't have a star's gravity, so we must find another way. So, what do you think? I would love to hear from you in the comments below. Have you ever looked up at the sun and wondered what powers that magnificent, life-giving furnace? The answer is nuclear fusion. It's the universe's ultimate power source. At its core, the sun is a giant reactor where hydrogen atoms, under immense pressure and heat, fuse together to create helium. This process releases a tiny amount of mass as a colossal amount of energy, as described by Einstein's famous equation, E equals mc squared. For eons, this simple reaction has powered every star in the sky. Now, imagine if we could create a miniature controlled version of that process right here on Earth. That is the incredible promise of fusion energy. Unlike nuclear fission, the process used in today's nuclear power plants, fusion is fundamentally different. Fission works by splitting heavy, unstable atoms like uranium, which releases energy but also creates long-lived radioactive waste. Fusion, on the other hand, does the opposite. It combines light, abundant elements, typically isotopes of hydrogen, called deuterium and tritium. Deuterium can be extracted from seawater, making it incredibly plentiful, and tritium can be produced within the reactor itself. Deuterium plus tritium yields helium nucleus, a neutron, and a release of energy. Building a magnetic bottle strong enough to contain a miniature star is one of the greatest engineering challenges ever undertaken. The ITER tokamak is a machine of superlatives. When complete, it will weigh 23,000 tons. It will stand as tall as a multi-story building. Its central component, a massive solenoid magnet, will be powerful enough to lift an aircraft carrier. Let that sink in for a moment. The sheer scale is necessary because the strength and precision of the magnetic field are everything. This field must be so powerful and so perfectly shaped that it can suspend the 150 million degree plasma in midair, preventing it from ever touching the chamber walls. The core of this magnetic cage is a system of enormous superconducting magnets. 18 D-shaped toroidal field coils. Each coil is 17 meters tall. They wrap around the donut-shaped vacuum chamber. These create the primary magnetic field that confines the plasma particles. A series of 6 poloidal field coils, rings up to 24 meters in diameter, positioned outside the main coils to shape the plasma. They keep it stable. Finally, at the very heart lies the central solenoid, a 1,000-ton magnet. It induces a powerful current within the plasma, heating it and further stabilizing it. Together, these magnets form an intricate, invisible cage. The term superconducting is key here. To generate these fields without huge power loss, the magnets must be cooled to cryogenic temperatures. The coils are made from a niobium tin alloy when cooled to minus 269 degrees Celsius. 4. Kelvin. Almost as cold as deep space. They lose all electrical resistance. This question gets to the heart of the paradox of fusion energy. While the plasma itself is hotter than the sun, the magnets that contain it must be among the coldest things in the universe. But what about the materials that sit right at the edge, facing the plasma's intense heat and radiation? The inner wall of the ITER tokamak, known as the blanket, must endure conditions found nowhere else on Earth. It has to withstand a barrage of high-energy neutrons and a surface heat load intense enough to vaporize any normal material. This is where some of the most advanced materials science comes into play. The blanket modules that line the vacuum vessel serve multiple functions. Firstly, they must shield the vessel and the superconducting magnets from the extreme heat and the fast neutrons produced by the fusion reactions. Secondly, they are designed to absorb the energy from these neutrons, which will be used in a future power plant to heat water and drive turbines. And thirdly, they will test the concept of tritium breeding. The blanket contains lithium, which, when struck by a neutron, transforms into the tritium fuel needed to sustain the fusion reaction, making the reactor self-sufficient. The most challenging part of the inner wall is a component called the diverter, located at the bottom of the vacuum vessel. The diverter acts as the tokamak's exhaust system, drawing impurities out of the plasma and handling the most intense heat and particle bombardment. The materials here face heat loads comparable to those experienced by a spacecraft re-entering Earth's atmosphere. To survive this, the diverter is made of tungsten, a metal with the highest melting point of all known elements. The tungsten diverter tiles are designed with intricate engineering to handle extreme heat loads. These tungsten tiles are bonded to a copper alloy heatsink that is actively cooled by pressurized water flowing through it at high speed. ITER is not just a scientific marvel, it is one of the most ambitious and complex international collaborations ever conceived. One partner calls it a global scientific partnership of unprecedented scale. China, European Union, India, Japan, Korea, Russia, United States, collectively represent over half the world's population and 80% of its GDP. The challenge of fusion is too large, too complex, and too expensive for any single nation. The collaboration model is unique. Contributions are mostly in kind, not cash. Each member manufactures and delivers specific reactor components. Japan, toroidal field coils. Europe, toroidal field coils. India, the cryostat. Korea, vacuum vessel sectors. Europe, vacuum vessel sectors. United States, the central solenoid. Components are built in factories worldwide. Then they are shipped to the ITER site in France for assembly. This creates a global network of scientific and industrial expertise. Companies and research institutions work together, sharing knowledge and pushing technology boundaries. Thousands of scientists and engineers contribute at the central site and in their home countries across metallurgy, cryogenics, robotics, and materials science. When people hear the word nuclear, safety is often the first concern that comes to mind. But it's crucial to understand that nuclear fusion is fundamentally different from nuclear fission. Fusion versus fission safety. No meltdown, limited fuel. The safety of a fusion reactor is built into its very physics. A large-scale meltdown is physically impossible in a tokamak. The fusion process requires incredibly precise and extreme conditions. If there is any disruption, loss of power, cooling system failure, breach in the vacuum, the plasma immediately cools down in seconds, and the reaction simply stops. There is no chain reaction to run out of control. Secondly, the amount of fuel in the reactor at any given moment is minuscule, only a few grams. Deuterium, tritium, enough to sustain the reaction for about a minute. This is in stark contrast to a fission reactor, which contains many tons of fuel, enough for several years of operation. The limited fuel supply in a fusion reactor means there is no possibility of a runaway power surge. The process is inherently self-limiting. The other major safety consideration is radioactivity. While the primary fusion reaction itself does not produce radioactive waste, the high-energy neutrons it generates can activate the materials of the reactor wall, making them radioactive. However, the activated materials in a fusion reactor would be fully recyclable or disposable as low-level waste within about a century. Imagine a world where our cities are powered by the same clean, inexhaustible energy that fuels the stars. This is the future that ITER is working to unlock. The primary goal of this grand experiment is to achieve a fusion gain, or Q value, of at least 10. This means producing 10 times more thermal power than the power required to heat the plasma. ITER is designed to generate 500 megawatts of thermal power from an input of just 50 megawatts. Achieving this milestone, known as creating a burning plasma, will be the definitive proof that fusion energy is a viable power source for humanity. If ITER is successful, it will trigger the next phase, the design and construction of demonstration power plants, or demos. These would be the first fusion reactors to actually connect to the electrical grid, converting the heat generated by fusion into electricity. Demos would be designed to operate continuously, breed their own tritium fuel, and demonstrate the economic feasibility of fusion power. They would serve as the final blueprint for the first generation of commercial fusion power stations, which could begin to come online in the second half of this century. A future powered by fusion would be transformative. It would mean a baseload energy source that is available 24/7, unlike intermittent renewables like solar and wind. The fuel, derived from water and lithium, is abundant enough to power civilization for millions of years. Ready to dive deeper into the matrix? Watch the next video here to see just how deep the rabbit hole goes. ITER is more than just a machine. It is a beacon of hope. It is humanity's boldest step yet toward harnessing the power of the cosmos and securing a bright and sustainable future for our world.